As far back as 1964, professionals have been able to predict the possible failure or need for overhauling of certain rotating equipment based on the speed of rotation as well as the amplitude during vibration. That has to do with maintenance and reliability. Fast forward to today, where there is a lot of available technology and standards and codes of practice. In this video, we are going to be looking at an overview of the considerations for the design of foundations for compound and complex vibrating equipment. In the past, we have taken a simple look at equipment foundation, which was for a simple block, as you can see in the image on the screen. But in this video, we are going to be looking at more considerations as pertain to the more complex concept for wider and larger trains of vibrating equipment. Hi there, and welcome to Catchment of Resources. In this video, we are going to be taking a look at certain considerations for the design of foundations for compound and complex vibrating equipment. A lot of the information is taken from the book Onshore Structural Design, while others are taken from Onshore Structural Design step-by-step calculations. Then we are going to look at a preview of multi-casing steam turbine, gas compressor turbine, combined gas steam power generation, skidded combined equipment module, and steps for foundation design of vibrating equipment. I understand that most of the design of foundation is done by civil or structural engineers. However, a basic understanding of the inner workings of these equipment can help with the actual design calculations for the supporting foundations. With respect to compound vibrating equipment, in most cases we may have probably a generator set, and that generator set is a vibrating equipment, and you place it on one foundation, and you can actually identify where the center of gravity falls. But in industrial application, you have multiple equipments which are installed at different locations, probably sharing the same shaft, but they are installed at different lengths along the foundation. So your consideration for design of the foundation is a little more complex than the generic center line for just one major rotating or vibrating equipment. So you can see in this screen, this image on the screen, and also the videos are playing along. You can see that we have like 4 segments of casing, but in the real sense, if you look at what is actually happening here, you have 3 segments of activity. The first towards your left, the red pressured segment towards your left or casing, is the high pressure steam chamber. So in this chamber you have compressors and you have steam turbine in it. In the middle segment you have the intermediate steam temperature, which is bringing in steam to compressors and turbines. And the last segment, which is the largest segment, is where you have low pressure steam, where this steam comes into the turbines and also rotates the center shaft. On the right is a real world application of this complex and compound steam turbine train. So looking further down at gas compressor and turbine. Gas compressors and turbine are similar to steam turbine. However, the fluid being used here is air. Air is taken in from the inlet and compressed. As it is compressed, it increases in temperature, and at some point a flammable fluid is ignited in order to heat up the air. And once you heat up the air, there are certain momentum that is generated within the fluid or the gas in this case, and it causes motion based on the pressure as well as due to the heat. It causes the wheels of the turbines to spin due to just the motion as well as the kinetic energy due to the heating of this fluid. So understanding the concept of both the gas turbine as well as the steam turbine in order to be more efficient, because when you're working with a gas turbine alone or a steam turbine alone, you may be getting efficiencies of about 30% to 40%. But when you have a combined cycle whereby you're combining gas and steam turbine, your efficiency can rise above 50% or probably to get up to 60%. because you are conserving energy. It's sort of like a circular energy system. So once you have heated the gases come out at high temperature. You use it to generate steam, and this steam goes to the steam turbine and also rotates the shaft, and then from the outlet it runs back, continuous cycle, one system benefiting from the other system. But in industrial application, they always take these things to another level. So in some cases, you will have a skidded combined equipment module. In other words, for example, if you look at this image here, you actually have different segments. So if you call this one segment, you call this another segment, and you call this point another segment as well. At this point, this is an air inlet. It's taking in air, as well as finding a way to filter the air and do a lot of things. Here you could then have your compressor and your turbine compressing and generating electricity by rotating the shaft of the generator. Here is now the outlet for all the gases, as well as a heating point of water in order to generate steam. So you can see here, so in this process you are going to be having the Rankine cycle and the Brayton cycle. The Brayton cycle has to do with gas, while the Rankine cycle has to do with an adiabatic process regarding steam and maintaining certain temperature levels throughout the process, dropping it and then raising it all over again in a continuous loop, which is the Rankine cycle. So step one in all of it, you need to know the type and size of equipment. So if you are running a gas facility or a steam facility, whichever you may choose, now describes which is project requirements. Then the manufacturer will now provide details regarding the weight of the equipment, the dimensions of the equipment, speed or frequency, center of gravity, eccentricities, tolerances, as well as other information. Secondly, you need to do a preliminary foundation sizing. So it's based on heuristics which have been done in the past, from where you will now get the dimension of the foundation. You can actually see this in this book, Onshore Structural Design, Step-by-Step Calculations. You can find how to do your heuristics for foundation sizing of vibrating equipment. So step 3 is to do a performance design and acceptance. So there are different ways that a foundation will support a vibrating equipment. For example, if you are installing a generator on top of a foundation block, this is the general and most basic type of vibrating equipment installation. So in that case, you are going to consider the point loads because you know where the center of gravity exists, which is a simple selection. Then you need to consider whether you are talking about static or dynamic analysis check. In most cases, for a centrifugal equipment, if your horsepower is below 500 horsepower, you are going to be doing only empirical analysis. But if it's greater than 500 horsepower, you need to do both an empirical and dynamic analysis. Similar for a reciprocating equipment, if it's less than 200 horsepower, you need to do empirical alone. But if it's greater than 200 horsepower, you do both of the approaches. So equipment on pedestal on foundation block. So this is another option. That is the point where this equipment is going to be transferring the load from the equipment to the foundation. Has now been decentralized from a central point to different locations. So in other words, those equipment are designed to be able to carry such load at those defined points, in which case you now need to do a load transfer for you to actually transfer this load to the center line or the center of gravity of the foundation block. So still within step 3, there are equipment that are installed on skid. For example, those power plants I showed earlier, where you have the air inlet, the gas turbine, the gas outlet, and all those other things, the purifiers and the rest, are installed on a skid which is a module that makes it easier for plug and play. You just carry the whole installation, you lift and you drop at the required location, and the installation is complete, which allows for quick and easy installation. So that's one option of skid type of foundation. So from this skid, because you are going to be getting a UDL, a uniformly distributed load along the skid, or point loads along certain points along the skid, you have to now transfer all of this load to the center line or center point of the foundation. So you will need to do some load transfer. So in all of these cases, I have not put it in all of the options, but you need to consider either a static analysis or a dynamic analysis in every case. So there's another option for equipment foundation block. In some cases, you could also have isolation pads being installed underneath the foundation block itself. So there are different options. So you need to look at the other options of how a foundation is constructed. But in this case, you are not adding an isolation block, which ensures that additional damping covers the vibrating equipment before it gets to the soil or maybe piles or whatever. So you have additional damping of the vibrating foundation. So lastly, you have equipment on elevated frame structure. So regarding foundation design and detailing, there are several highlights which I've made here. So first of all, the shaft is the central location for all of the equipment, whether it's the compressor, the turbine, the generator, and the other equipment. They are all on the same axial line, which is the shaft center. So it's possible that sometimes you can have misalignment or deviation or eccentricities, which are designed for, but all those eccentricities do not go beyond a certain, in terms of millimeter, they do not go beyond a certain amount in distance. I'll provide a sketch here shortly. You can also see that when you are selecting your foundation, the foundation has to coincide. The center of gravity of this foundation on the horizontal plane needs to coincide with the center of gravity of all of these vibrating equipment. So once you're able to locate this center point for both the equipment and the foundation, then the calculations have been simplified. So you have less eccentricities, which can lead to additional moments. So for example, let's say we have this as the shaft, and we have the first stage, which is the high pressure steam turbine, second stage, which is the intermediate steam turbine, and the last stage, which is the low pressure steam turbine. So you can see that from here, all of them are maintaining the same axis, but the rotation in terms of revolutions per minute will vary along each of these turbines and system. Then the generator comes at the end. So these variables in terms of the variation in revolutions per minute is now what we are going to check for in the design, is what we are going to check for in our performance analysis of how the equipment is going to run. For example, you don't want to have resonance between, so you will need to find out the various rotating speed. And whatever foundation block is being designed, you need to ensure that the frequency, the natural frequency of that foundation block does not at any point in time coincide with any of these frequencies from the vibrating equipment in order to avoid reaching resonance. So there is a certain threshold which is about 1.2 above the range and 0.8 below the range in order for you to ensure that there is no resonance occurring between the foundation and the vibrating equipment. So with respect to modeling, when you are going to model this foundation block in a software, any software can be used for this analysis. You need to consider that, assuming you are using isolation pads, that these isolators are going to contribute in terms of spring effect. Then also it's going to contribute in terms of damping effects. So those vibrators, they're actually sort of like elastic materials that helps to reduce the effect or to slow down the foundation as quickly as possible, which is essentially what damping is. When you are doing your model for the spring, you are going to consider both the soil and the isolators. So you are going to sum them together, algebraic sum, and you use the equivalent for your analysis. For the model, for the damping, you are going to sum them directly and you get what your damping is going to be. So you are going to consider probably a Rayleigh frequency for your dynamic analysis on your software. So once that foundation block has been designed, you'll be able to get your foundation details and reinforcements. And seeing that a vibrating equipment is a continuous process which is back and forth for multiple and varying stresses acting on the foundation, you need to design for fatigue. So there are also rules for designing for fatigue, the number of cycles that this foundation block can handle. So it can let you know how long it's going to last before a maintenance will be required. So probably you are talking of over 1 million cycles of this vibration as a lifespan or more. So you can then do your finite element analysis after generating a model based on several of these concepts. So this is just a model of the isolation part. So in some cases where you have, let's say the facility where you have an elevated platform, the working platform, but they want this vibrating equipment to flush with this elevated and working platform, it means that the foundation has to go down. In which case, you now also want to have isolation pads so that you are not feeling any effect, because this is an enclosed environment. So you now install isolation pads. The reference for where this was gotten is actually in the description. So in some cases, once you have installed these pads, you now construct the concrete block. There are also instructions on how this construction is going to take place because of the formwork requirements, and not to compromise the pads you have installed by having concrete damage them. So there are construction instructions. Once you have installed them, in some cases you will now install an expansion joint between the general working platform and this foundation block, which is how it is done. So this is just a simplified model of what the foundation is going to look like when you are doing an analysis of the foundation's interaction with the soil. So you need to get the soil resistance spring for all directions as it pertains to this model of the foundation block. And in order to get higher resolution or accuracy in the calculations for finite elements, you need to use much smaller element dimensions. So it all depends on what control you are using and level of detail you want, as well as convergence, because the more elements you create, the more expensive your program is going to be. In other words, it's going to take up more space, it's going to take longer to actually run your analysis. So the last step is documentation. Once all of this design has been done, you need to document the design in a simplified manner that people who are going to approve it, people who are going to carry out the construction, or for verification in a way they can actually understand the designs that have been done. Also, construction details need to be generated to know the level of constructability. You need to be sure that it's possible. You don't want to create a situation whereby something cannot be constructed because you cannot access where you want to do the construction. So you need to show a proof of the constructability. Then, as well as installation details, what is the weight of this equipment you want to install? Do you have the right lifting equipment to carry out this job? Is the crane of the right capacity? Are there openings for you to install the equipment? So such details also need to be included. Then you need to consider at some point the handover or commissioning of such equipment foundations. Then you need to provide user manual depending on where you are. So it depends on where you are in the value chain of either design and construction of vibrating equipment. Thank you for watching this video. I hope the information provided here is going to be useful for you to do your own personal study and research. This is Catchment of Resources, where we create for better living.